it does indeed give me great pleasure to present to all of you on this technology. It's been many years in the making, and I'm very proud and pleased to say that it's now making its way into smartphones and chips, GPS chips. And I'll be able to show you over the course of the next 25 minutes or so exactly why it's clever and how it works so well. I want to start by thanking all the team back at FocalPoint Positioning. They have done a huge amount of work in actually making this technology come to life and moved it from a vision and an idea and equations on a board to production grade software that's being deployed inside devices. So congratulations to you all for all your hard work. So the story of supercorrelation begins with one of these. I'm sure you're all very familiar with what global navigation satellites look like. This is a GPS Block 1. Other global navigation satellite systems are available. And supercorrelation is applicable to any of the signals from these sorts of platforms and any digital positioning signal of any type. A correlation is the most important process that goes on in your receiver. It is how you detect the signal from the satellite in order to then use it to calculate where you are. So these satellites are fundamentally very expensive and very clever clocks in space, and they're transmitting the time over and over to us down here on Earth. And in order to pick up the signal from them, we know the code word that these satellites transmit. That code word is inside your GPS receiver. Every satellite has a unique code word, and what your receiver does is it goes searching for the satellite using that code word, using a process called a correlation. It tries to line up in frequency and time its local copy of the code word with the copy that is hopefully buried in the radio data that you're picking up from space. And the correlation process will give you this spike in power when you have actually detected the signal from space. And this is what we call a correlation peak. And measuring the exact moment that correlation peak arrives is how you work out where you are. And it's where all of the errors in where you think you are can be as well. And that's what we'll get to the bottom of in the beginning of this talk, as we look at how a correlation peak can be badly corrupted and how a supercorrelator stops this from happening. So here's a nice little cartoon of that same correlation peak. So we detect this pulse coming from the satellite, and that's how we start to work out where we are. And you'll see this scale along the bottom in meters here. These peaks, these correlation peaks, have effectively a fundamental width. The radio signal, when it reaches us, it takes some amount of time for us to actually detect it and measure it, and that manifests as the pulse having some physical width in space. And the problem that we're going to solve is the problem of this peak becoming distorted, giving you an incorrect range measurement to the satellite. So the first thing I'm going to do is give you a really quick whistle-stop tour of how multipath interference occurs in the first place, and then how supercorrelation solves it. So we start the story with the correlation peak we want, this beautiful, clean line of sight pulse that we've picked up from space. But the problem is that these radio signals bounce around the environment. They bounce off buildings and cars and people and trees, and multiple copies of the radio signal you want can arrive at your receiver with different delays and amplitudes compared to the line of sight, which is the only one you care about. So this cartoon is showing now the line of sight pulse that we want and a delayed echo as well, here in pale blue, that's arriving with 300 meters of extra delay. So it's bounced off a building and has taken 300 meters extra path length to reach us. And when the delays are so big, they're not that much of a problem. We can actually independently resolve the line of sight separately from the reflected copy. But if you consider a problem like driving towards a building with the signal bouncing off it, then what this little animation is going to show next is, of course, that reflected echo actually gets earlier and earlier and earlier and overlaps more and more and more with the line of sight one. So the problem is how these signals interact with each other. So you might think that they simply add together. So this is a cartoon of a simple and incorrect guess at how the signals from multiple paths interfere with each other. So as that reflection is getting closer and closer to us, you might think that the summation, the total pulse, is just a simple addition of the two, and that the peak of the line of sight and the non-line of sight is simply some average of them. This is unfortunately not the case. It's much more complicated than this. The signals are radio waves. They have peaks and troughs, the crests of the waves that are carrying the signals to us. And actually the phase of the signals when they interact with each other is really important. And I'm going to represent the phase difference between the line of sight and the non-line of sight signal by having that blue echo now wind in and out of the screen. So I haven't done a very good job of representing 3 dimensions here, but I want you to actually picture this as being that blue peak is of a fixed height, and it is rotating around the line, coming in and out of the screen in front of you. And that represents the phase difference between the line of sight and the non-line of sight signal. So the two are actually wrapping like this against each other when they combine. And if I pause at just the right time, like, oops, that, let's try again. I'm trying to catch just the moment when the, that'll do. I was trying to catch the moment when the red pulse is at its most distorted. What you can see is that there are now 2 humps here. And if you look very carefully, if I try to catch it again, that's much better. When the line of sight and the non-line of sight are in antiphase, when they're actually completely out of phase with each other, there's this deconstructive interference that means that you get these 2 peaks. And if you look carefully, the line of sight peak is actually later than the loudest peak in the multipath corrupted total correlation peak. And indeed, this peak here is later than all of them. So the combination of the line of sight and the non-line of sight signal gives us a correlation peak with maximum value that isn't actually either of the maximum positions of the line of sight or the non-line of sight. And this is one of the biggest problems with multipath interference. It's one of the most surprising things that people come across when they first start to study this phenomena. You can combine 2 signals which are only a couple of meters apart in reality, and the interference between them can cause errors of actually hundreds of meters. And that's what this animation is now showing. So we've now gone to a real extreme example. I'm now interfering about a dozen signals together of different amplitudes, delays, and phase rotations. And what this represents is effectively driving down a road, and the buildings around us are all reflecting a satellite signal down towards us. Now, in this simulation, none of these reflections are any further away than 20 meters extra path delay. So you might hope, you might think that the largest error you'd get on your GPS range estimate is only 20 meters. But in actual fact, what you can see as we're driving down the road is that the error in distance to the satellite that we're calculating using the correlation peak can actually be almost 100 meters in either direction. And in fact, the next plot shows the histogram of those errors. So the most extreme errors are close to 100 meters apparently early or late compared to the true line of sight. And this is, as I said, one of the biggest problems of all in radio positioning. You can have a very short delayed signal, a reflection from an object that's only a few meters away from you, and it can cause 100 meters or more of positioning error. So this has been a major problem for radio positioning for decades. And the killer question is, how can we design a system which is sensitive to only the line of sight pulse that we're interested in and blind to all of the non-line of sight stuff that we don't want to detect? And answering this question is what supercorrelation is aiming to do. So let's dive in. I'm sticking with cartoons and diagrams. You'll be pleased to know there's no maths in this talk, although of course there's a huge amount of maths underlying all of this. So the satellite transmits its code word over and over again, and that's what these little blobs are representing. And it transmits it on a certain frequency. And the textbook view on how a GPS receiver works is that you take a local copy of this code word in exactly the form that it's written down in the textbooks as its pattern of 1s and 0s, and you use the radio receiver to lock on to the frequency that the satellite is transmitting on, and you search for the maximum power that you can find in that process. Now, in reality, life is actually much harder than that. There are subtle errors in the data that you pick up from the satellite. There are a number of frequency variations in the radio signal, and these are mainly caused by your own motion. So because you are moving through space, as you are picking up the radio signals, you cause Doppler shifts on the radio signal you're picking up. The satellite itself is also moving through space. The satellite's clock is not perfect. They are atomic clocks, but they're still not perfect clocks. And more importantly, the little clock inside your smartphone is really low quality. And that causes a lot of phase variations as well. That also causes these contractions and compressions in the apparent frequency that you're picking up. And so immediately we have this interesting situation going on where the correlators we use at the moment inside the GPS receivers are very simple. We've been using the same approach for decades. In reality, the signal is actually much more complicated, but we get by with a very simple textbook correlation. The interesting thing, however, is that these very subtle differences in frequencies and phases change if the signal bounces off a building. So the pattern of Doppler shifts caused by your motion as you move through a city cause the line of sight signal pattern to be subtly different compared to the one that has bounced off a building. And this is what supercorrelation does. We use the inertial sensors in the phone, we use advanced clock modeling, we combine data across different satellites at once in a single estimator of the clock error in order to determine this exact pattern of complicated behavior. We predict what that pattern should be, and we use it to build a unique supercorrelator for this moment in time. We actually build a new supercorrelator every second. Each time it is different to the one in the textbooks. The textbook correlators, meanwhile, are effectively just as bad at accurately picking up the line of sight signal as the non-line of sight. They're not really perfectly tuned for either. And that's the problem. That's why they've always been historically picking up the stuff you don't want as well as the stuff you want. They've never actually been tuned properly to the stuff you want. So normal GPS processing uses very small sequences of exactly the textbook data to keep trying to pick up radio data. A key difference between us and between supercorrelators and old correlators is that we use a very long sequence and we tailor these phase patterns correctly. It sounds easy. In practice, it's very hard, which is probably one of the reasons why it's never been done before. It's important to build supercorrelators that are as long as you possibly can. We build ones that are over a second in length. That means we're gathering a second's worth of radio data and turning it into one measurement of the distance to the satellite. To put that into context, normal GPS processing is using about 20 milliseconds of data and then averaging 50 of those very small measurements together every second, whereas we're processing 1 second's worth of radio data in one go. We must compensate for the motion of the receiver during that second to the centimeter, and I'll show you in a moment how we can do that. But certainly a big part of that is using accelerometers and gyroscopes, which are conveniently in every smartphone and in every wearable today. I'm not getting in today about how we compensate for the poor clock behaviors inside our receivers. That's more than I have time to talk about today. And so I will simply use the 2 words clever algorithms to cover off how we solve the clock problem. And one of the other challenges to supercorrelation is that the data that comes from the satellites has navigation information on it. and you have to strip off that navigation data to supercorrelate. And there are various ways you can do that. Conveniently, some modern signals don't have any data on them at all. They're called pilot channels, so they're great. Galileo, for example, transmits pilot channels, but there are other ways that we can strip off the data modulation. And a key to all of this is actually modern GPS receiver design. So we couldn't have actually done this about 10 years ago. 10 years ago, the way that the receivers were designed and the way that the chips were designed were that they were a monolithic silicon design. Inside that chip were a load of physical fuses that couldn't be changed once they had been designed, and that chip had been burned into silicon to do its job. Nowadays, GPS receivers actually contain a little computer inside them, a flexible central processing unit, just like the computers in your laptop, that can run software just like your laptop can. And this is key. This is how you can build supercorrelators. You need to effectively reprogram a little bit of your GPS chip every second, and that's what we're doing. And so we can only do that because modern GPS receiver designs contain digital signal processing units today that can run software. So I'll give you a quick glimpse into centimetre-level motion compensation. For something like a car or a plane or a drone, this is less of a problem because those platforms will often be traveling in relatively smooth paths, typically moving on quite straight lines and so on. But for humans carrying smartphones, in 1 second, you can move the antenna of that GPS chip through multiple wavelengths in a non-linear manner. And we must compensate for that. So FocalPoint have an entire team of world experts in human motion modeling and motion compensation. And some of the cleverest things we've done in the last 5 years have been on motion compensation as opposed to being on GPS signal processing. And these little movies show you the power of what we can do. So that's a smartphone on Henry's arm there, who is both an excellent model, an excellent runner, and an excellent expert in human motion modeling. You can see every little bump and wiggle on that red line, reconstructing the bump and wiggle of the smartphone on his arm. And one of the biggest challenges of using inertial sensors for monitoring motion through space accurately is when people want to move those sensors around separately from the body they're attached to. And you can see here Henry moving that smartphone around between different pockets. And a naive approach to doing motion compensation would break when you detach the sensor set from the body and move it to a new location on the body. And so that's one of the key problems we have solved as well. So this little wiggly line that you're seeing that's monitoring the motion of the phone to the centimetre level is being used inside the receiver to perform these Doppler compensations and build the supercorrelator. So you're all now experts in correlation peaks, thanks to the first section of this talk. These are some real ones. So this is real data from some real experimentation. The yellow dots on here are the correlation peaks from traditional standard GPS processing. In fact, they're the ones that we've been given by partners from their own GPS chips. The blue line is the supercorrelation version of the same data. The red marks that you can see, that red shape represents a perfectly clean template of a correlation peak. So whenever these red X's fit correctly on top of the blue, that's the confirmation that we completely removed any multipath and the signal is perfectly clean. At the top here is an example of gathering data from the top of a hill with no buildings around us, and normal GPS processing gives you the same answer as a supercorrelator, a nice clean signal, because there were no reflections. However, look at this one, and this is from inside an urban canyon in a city, and here's a nice corrupted multipath peak, like I was showing you earlier in the simulations, and the supercorrelator has extracted just the line of sight component of the data and has actually washed away and removed all of the non-line of sight stuff. And so we've got a nice clean line of sight signal. you can actually see that this is the noise level, the noise floor of traditional processing as well. Supercorrelation boosts the signal on the line of sight and it pushes the noise down. So we can actually see signals that are weaker than normal processing can even detect. And this is a good example of that. This is an example where there's a nice clean looking signal arriving. In fact, it looks like it's a very good candidate for a line of sight based on how clean it is. But actually the supercorrelator has found below this noise floor an earlier clean correlation peak. And the line of sight signal is actually about 10 times down on the noise floor of normal signal, normal GPS processing. They were some GPS L1 signals. There is also new signals transmitted on the L5 band that have higher bandwidth and so narrower correlation peaks. This is great because that itself is some resistance, some protection against non-line of sight signals, but all of the benefits of supercorrelation still apply. An L5 correlation peak is only 60 meters wide, but still gets multipath interference at that level, which we can clean up. You still get examples where you can't even see a weak signals coming through a building with traditional processing, and supercorrelation can go down into the noise level and pull out the actual signal at a much higher sensitivity. And here's just an example of another one where there was what looked like a perfectly clean L5 signal, but we found a weaker earlier version, the line of sight buried in the noise. And that's because in these sorts of examples here, the line of sight signal was coming through an object to get to the receiver. And we've managed to go and find that really weak attenuated signal that's come through an object to get to us. So here's some data from driving around. This is London. Canary Wharf is the most skyscraper dense part of London. And this is driving around with GPS L1 only positioning with normal processing shown in red and our SGPS supercorrelation technology shown in blue. And the plot on the left is showing the histogram of the errors of the two. So FocalPoint have returned position fixes with a 95% confidence bound at 13 meters, whereas traditional processing's 95% confidence bound is out at over 100 meters of error. And of course, you can see on the map the times when the normal positioning was really bad because of the reflections in the urban canyons. This is pictures from the same journey, and this is the actual ranges to the satellites detected using the correlation peaks. And so you saw a simulation of this sort of thing earlier, where the correlation peak was causing all of these large plus and minus 100 meter scale errors. These are now real data as opposed to simulated. So this is results from a partner company's chipset showing the sheer amount of multipath interference they were suffering on that London drive, where their estimate using traditional processing of the correlation peak was giving them errors out at sort of 100 meters in either direction and so on. The very same data processed with a supercorrelator looks like this on the right. All of the multipath interference has gone. We're not locked onto any non-line of sight signals at any point. You can see that all of these colored lines representing all of the different ranges to all of the different satellites are all following this interesting looking trend. That's actually the final clock variations that we're observing inside the GPS receiver. So these variations that remain are basically due to the stability of the clock inside the smartphone. And the navigation engine processing removes that last bit of error when it solves for position and time inside the navigation engine. I'll show you a little bit more on the measurements that we improve with a supercorrelator. I've talked a lot about ranges or pseudo ranges, which are the distance to the satellite. The Doppler measurement, which is an estimate of the frequency that you're picking up the signal on, reveals your speed and your velocity, and it allows the receiver to give you a velocity estimate as well as a position estimate. And what this is showing is a section in that part of the London drive where we've been stopped at some traffic lights, and so there's been zero Doppler shift. The black line you can just about see here is the truth. So the black line is showing what the Doppler shift to this particular satellite should have been based on when we used the accelerator and the brake and which way we were pointing in London and all of that sort of thing. The blue line that you can see just about beautifully following the black line is the supercorrelator estimate of the Doppler. And as you can see, it's correct. It's following the true black line. The orange line is the Doppler measurement according to traditional GPS processing. And as you can see with a reflected signal, you're literally getting a reflection of the Doppler. You're being told that you're traveling in the opposite direction than the direction you're really traveling in. Because what's happened here is, as we've moved off from the traffic lights, the traditional GPS processing has been attracted to a reflected signal and is tracking a reflected signal that's bouncing off a building. In reality, the line of sight has been blocked by a building, and the supercorrelator has maintained lock by staring through the building at the weak GPS signal coming through it. And you can see that here in the signal strength plot. So as we correctly follow the true frequency of the satellite, we are returning a very weak signal. We've got low signal strength, whereas traditional processing is returning a high signal strength, and that's because it's locked onto a non-line of sight signal bouncing off a building. So we give you the true, a supercorrelator gives you the true pseudo-range measurements, the true frequency measurements, and a truer estimate of the signal strength of the actual line of sight signal. I'll show you some more clever things you can do with supercorrelators. So this picture here is an example of a sky plot when you see where the different satellites are in the sky above you. So you might be used to seeing pictures like this when you look on your smartphone and it shows you which satellites are in the sky. Now, what we can do with a supercorrelator is scan the entire sky for energy coming from different directions. And so that red dot there represents satellite number 23. And a supercorrelator normally is just telling us information about that part in the sky. But we can build a whole bank of supercorrelators. We can build these complicated phasor sequences to actually look in all of the directions around us. And we can measure the energy coming from different directions. So this is an image of the directions around us in north, south, east, and west, that energy has come to us from different directions in the environment. So we can actually image where the buildings are around us by seeing where the strong reflections are relative to where the satellites are. And we generate these unique outputs that you don't get with normal GPS processing. We can image where the energy is coming from around us from each satellite using supercorrelators. You can use that instead of a magnetic compass. So because we know where the energy is coming from, because we know where the satellites are in the sky, we can actually determine our heading through space with each of these 1 second supercorrelators. And we can do that with just a few degrees of heading error. And I will quickly end with just showing you one of the neatest things you can do with supercorrelators, which is to provide anti-spoofing capabilities. So this is a simple experiment where we've driven around a car park. We have done real world spoofing trials, but I can't show you any of that data. It's not public data. So this is information from a simulated spoofing attack. So spoofing is when someone tries to transmit fake GPS data in order to disrupt a GPS receiver. So we were driving around this car park. We've gathered all the data, taken it back to our lab, and injected afterwards in the lab a fake spoofing attack. Now, a normal GPS processing stage has been disrupted by the spoofing attack, and that's the blue line on here. The red line, which is correct, showing us driving along the roads in the car park, that's the result of the supercorrelator ignoring the spoofer. And it simply was looking in the correct parts of the sky for the satellites and ignored the spoofer that was transmitting from this low building over here. And I'll very quickly show you the spoofer being revealed in Skyscan plots. So each of these circles, one per satellite, is showing you the energy coming from different azimuths and elevations around us. And the spoofer is turned on now as we're driving around the car park, and you can see this energy band that has appeared that's common to all of these Skyscan plots. and that's revealing that the spoofer is south of us. And we would actually be able to use Skyscan information to localize, to locate that spoofer, that illegal broadcast of GPS in the environment. So in summary, there's an awful lot of things we can do with supercorrelators, and there's probably a lot of stuff yet to come that we haven't even thought of yet. But my rapid summary is we can use them to remove multipath interference and provide a much more accurate GPS fix in urban environments. We can improve the integrity of GPS and GNSS receivers by giving you that honest understanding as to which signals are line of sight and which ones aren't, and allowing a navigation engine to throw away the signals that are not line of sight. And that gives you the highest accuracy first fix you can possibly achieve. We can ignore spoofing signals in the environment without needing encryption, authentication, keying, controlled radiation pattern antennas, any of that expensive stuff. We can also locate spoofers, which I think is relatively unique. There are not offerings for GPS receivers to locate spoofers in their environment at the moment. We can use Skyscan to provide what's called 3D map aiding, where you use the signals that have bounced off buildings in order to improve your estimate as to where you are. We can work out your heading through space with 1 second of GPS data without using a magnetic compass. And for those of you who are familiar with RTK systems and how delicate they are, but how important they are for giving centimetre-level positioning, supercorrelation can aid an RTK system by ensuring it's only processing the line of sight data. And coming up on our roadmap in focal point positioning is applying our supercorrelation technologies directly to RTK itself and providing a supercharged version of RTK. So you can watch this space for news about that in the near future. And with that, I shall happily take any questions that you have. Thank you very much.